Hi, my name is Michael Woldridge. I am currently enrolled in AGR 214 Numerical Methods for Engineers in the spring semester of 2021, and the instructor is Dr. Hans Chapman. And today I'm going to be doing a MATLab tutorial solution manual related to Physics 1 and Engineering Dynamics. The topic itself is position as a function of time. The concept and relevant formulas are shown on page 38 of the text Physics for Scientists and Engineers on the 10th edition by Surway and Jeanette. As you can see, these formulas here are can find the final position as a function of time. Both of these can be used, but mainly on the second one is the one we're going to be focusing on. The example from the text on page 40 is a two-part example solving for the acceleration first, and then to solve for the final position. So solved problems are as shown here. If a particle has an initial velocity of 12 feet per second to the right and initial position of 0, determine its position when time equals 10 seconds and acceleration is 2 feet per second squared to the left. So that would mean it'd be negative. As shown in the formula here, it would plug in the numbers. So 0 plus 12 times 10 plus 1/2 negative 2 times 10 to the square equals 20 feet. Or we can plug into the MATLab numerical solution here of all these this simple coding of just typing in the formula and putting in the variables up there in the function file. Say the file has position position m and invoke the function return to the command window and type in position and then the numbers that correlate to the different variables. So in this problem would be 0, 12, 2, and 10, and the result would be 20. In the next tutorial problem, there will be two cars. Car B is traveling a distance d ahead of car A. Both cars are traveling 60 feet per second when the driver of car B suddenly applies the brakes, causing his car to decelerate at 12 feet per second squared. It takes the driver of car A 0.75 seconds to react, which is the normal reaction time for drivers. When he applies his brakes, he decelerates at 15 feet per second squared. Determine the minimum distance d between the cars as to avoid a collision. And so you go over the analytical solution, which for car B, you go for the velocity and position for car B, and then for car A. And then you solve for t by combining the velocities of both car B and A and put them equal to each other to solve for t, which will be 3.75 seconds. And then you grab that value you just got and put it into the position of car B and A, which are equal to each other, and you would get 16.9 feet. Or you can just put in the numerical solution of typing in position and then the variables that correlate to the variables, so 60, 15, 3.75, and you would get the result 16.9. The next problem, it would be this is on the experiment that was done and March 19th, 1954 by Colonel John Papp. He rode a rocket-propelled sled that moved down a track at a speed of 632 miles per hour. And then him and the sled were safely brought to a rest in 1.4 seconds. You then convert on the miles to meters per second for convenience, and then you use those variables that you're given to find the constant acceleration, and then once you find the constant acceleration, you would then plug it into the final position formula that we were going over, and you would get 197.8 meters, or you can just plug it into the position file where initial position is 0, 282.5, constant acceleration at negative 202, and time being 1.4, and you would get 197.8. In this tutorial problem, a member of the volleyball team jumps straight up in their center of mass has a speed of 2.8 meters per second as they leave the court. How high above this point is their center of mass at the following times? Enter your answers in meters, ignore its effects of air resistance, and assume the initial height of their center of mass is 0. So then you grab this schematic equation to solve for vertical position and center of mass. Plug in the variables that you are given, and you would get 0.231 meters. Or you can just grab the variables that you are given and plug it in and get the exact same answer. And then for our last problem, a particle starts from point O and accelerates uniformly for 8 seconds at a constant rate of 2 microseconds until it reaches a point B. Calculate 1, the velocity at point B, and the distance covered. In this, you let u be the initial velocity, t being 8 seconds, and the final velocity, or the velocity at p, and the acceleration. First, you solve for the first part, and then you solve for the second part after getting which is 64 meters. Or you can just plug it in 0, 0, 2, and 8 and get 64. In conclusion, this project shows how important knowing how to solve for a position as a function of time can be applied into real-world solutions using MATLab. This kinematic equation can be used in several different situations as shown in the above problems. Overall, it can be used for testing new vehicles, predicting particle travel distance, and much more. It is even more utilized in MATLab as someone is able to change the variables easily and save hours of time that had been spent on analytically solving the problems one by one. Thank you.